Thank you, Juan Miguel, and it's great to be back at QHack. I think I had such a great time at QHack last year, and I've been counting down the days to present at this QHack. Like Juan Miguel mentioned, I'm one of the lead developers of Penny Lane here at Xanadu, and while I do have a mental map of Penny Lane and how it works, I think one of my main goals is to give that to everyone else and have everyone have a overview and a mental map of how Penny Lane works, how they can use Penny Lane to do the best research and exploration with quantum computing and quantum machine learning, and how they can contribute to it and develop and give back and make Penny Lane greater than what currently. So I'm excited to get started. So as mentioned, my talk today is on differentiable quantum transforms, and this is a new way of thinking of programming quantum computers that we're trying to build up in Penny Lane. I'm excited to talk about this. So before we get into differentiable quantum transforms, I have to take a step back and introduce a concept known as quantum functions. So a quantum function is the core unit of computation that you're using if you're using a software framework like Penny Lane. And let me explain a bit what it is. So a quantum function, it's like any other Python function. It's a function that you define in Python and it accepts, in this particular case, classical floating point parameters. Now, what makes a quantum function quantum is that inside this quantum function, there are quantum instructions. And these quantum instructions, they could be gates, they could be measurements, they depend on these floating point parameters that you pass into your quantum function. And another key concept here is that the quantum function always returns measurement statistics. And why does it return a measurement statistic? This is because we want it to return something that's deterministic. So for the same input parameters that you provide to your function, you're guaranteed the same output up to noisy short noise coming from noisy hardware. So I mentioned that this is one of the core paradigms in Penny Lane. Let me show you what I mean with a quick introduction. So this is something that those of you familiar with Penny Lane might already be familiar with, but if not, I'll show you here. So here I'm just importing Penny Lane. I'm creating a quantum device, which can be a hardware or simulator. And now I'm creating my quantum function. So this is a function that takes in two parameters, x and y, and now I'm applying two quantum operations, the rotation around the x-axis gate and the ry gate. And finally, I'm returning that measurement statistic that I mentioned before. And so once we've defined this quantum function, we can use it like any other function in Python. You can interface with SciPy, you can interface with NumPy. Here I'm providing two floating point parameters and I'm getting my output. What makes it different though is that this quantum function is being evaluated on quantum hardware by applying quantum instructions that depend explicitly on these two floating point parameters, 0.4 and 0.5. So that's the basics of a quantum function. Think of it as a Python function that accepts standard Python objects, returns standard Python objects that at its core it's performing its computation on a quantum device. So now that we know what a quantum function is, we can take a step further and think about differentiable quantum functions. So for a bit of formality, here's the definition we have for a differentiable quantum function. Say we have a quantum function f of theta. So f is the quantum function, and theta I are the input parameters that we're passing. So in the previous example, those were those two floats, 0.4 and 0.5. Now, a quantum function is differentiable if the partial derivative df over d theta I is defined for all input parameters to our quantum function. So basically, if we take our quantum function and the derivative is well defined for each of those input parameters with respect to the output measurement statistic, we have a differentiable quantum function. So that's all well and good, but can we take this formal definition of a differentiable quantum function and actually use it with hardware that we have available? It's not often sufficient to simply simulate this. As the number of qubits or y's in our model grows, we're no longer able to compute the gradient as we would in any standard classical computer setting. Instead, we want to be able to use the same quantum hardware underlying the quantum function to also compute the quantum gradient. So luckily we can. And for those of you who watched QHack in the previous 2 years and are familiar with penny lane, you might be familiar with this concept as well. That given a quantum function, so here we have a quantum function that simply is mathematically represented by a quantum state that exists on our quantum device, the parameterized quantum options inside our quantum function, and an observable that we wish to measure a measurement statistic of. So in this case, we're measuring an expectation value. So this is just a fancy way of mathematically showing the definition of a quantum function in the previous slide. So a really neat result that we've helped to develop here at Xanadu and also built directly into penny lane is that if you have a quantum function where the parameterized quantum instructions that exist inside your quantum function are being applied on the quantum device are such that they can be written in this form, the exponential of a generator, where that generator has equidistant eigenvalues, then there's this neat result called the parameter shift rule, where the derivative of that quantum function with respect to the input parameter can always be represented as a summation over that quantum function itself being evaluated at different shift values with different coefficients. And this is a really neat result because it means that the quantum function that we started with, we can simply reuse that existing quantum function to compute the gradient. And all we need to do is we need to take that quantum function and evaluate it at different points, take a linear combination of those different evaluations with different coefficients, and construct that linear combination, and that gives us the gradient. So this is a neat result because it means that the hardware we're using to evaluate the quantum function can also be used to extract the quantum gradient. For the Pauli rotation gates, this reduces to a very common two-term rule. So this is something that some of you might be familiar with. If you have a gate that's, for instance, a rotation around the X, Y, or Z axis, the RY, RX, and RZ gates, you can extract the quantum gradient of this particular type of quantum function simply by evaluating this quantum function at 2 points, taking the difference, and dividing by this factor 2 sine S. For more details, I'd like to, if you're interested in reading more about this, I'll point out a paper that we recently put up on the archive that goes into this in more detail and explores the theory and the constraints and the possibilities of these general parameter shift rules for quantum gradients. And I'd also like to take this moment to point out that there's a talk coming up in QHack as well to explore this in more detail. So definitely do join as Cody explores the theory behind the general parameter shift rules for evaluating quantum gradients on quantum hardware. A really, really cool talk. Make sure not to miss it. But back to this idea of differentiable quantum functions. So we've defined what a quantum function is, and we've seen that the most common quantum functions where the quantum instructions satisfy a particular form, we're able to differentiate that on quantum hardware. So the quantum function is also a differentiable quantum function. So that's great, but we typically want to do a bit more than differentiating a single quantum function. We want to be able to build models that arbitrarily mix and match quantum functions and classical processing. So if you have a look at this graph here, we have a superconducting qubit quantum function, a quantum photonic chip, quantum function, and amongst that we have various classical functions, neural nets and GPUs. So we can build as arbitrary models as we want. And the really nice thing about this process is we can arbitrarily mix quantum functions and classical functions, and we can make the entire thing differentiable and trainable. And the reason we can do this is because there's a wealth of amazing auto differentiation and machine learning tools available in Python. So tools like TensorFlow, PyTorch, and JAX, which enable backpropagation and auto differentiation in Python. We can use penny lane to integrate these tools with the differentiable quantum functions we were just talking about. So we can use penny lane to define quantum functions we want to run on quantum hardware, and arbitrarily mix and match that with classical processing, and then train the entire pipeline with TensorFlow, JAX, and PyTorch. So I've just got a quick example to highlight this possibility. So in this example, I'm importing Penny Lane. So this is going to allow us to build our quantum functions, and I'm importing JAX. So in this particular example, I'm going to use JAX to do the backpropagation through the hybrid quantum classical network. So I've created a simulator device, and now I'm creating my quantum function. So I've just specified interface equals JAX because I want this quantum function to connect to JAX for backpropagation through our model. So I've got a quantum function that applies some instructions, quantum instructions, and returns a measurement statistic, in this case, the probability. So now that I've done that, I've created a JAX array, and I can evaluate this quantum function. And you can see that I have a JAX array going in and a JAX array going out. So this is interfaced directly with the JAX machine learning library. So this is where it gets more interesting. I can do something really arbitrary. So here I've created a cost function. And in this particular cost function, I'm doing a mixture of evaluating a quantum function, but I'm also pre-processing the weights just by taking the sign of them. And then I'm post-processing the output of the quantum function by taking the cosine, squaring that, and summing that. So I've got a bit of a eclectic mix here of quantum processing and classical processing. And this cost function, I'm evaluating that with the weights again, getting output. And the really neat thing is you can then evaluate the gradient using JAX. And JAX is performing the backpropagation through the full model, and Penny Lane is taking over at the quantum component and providing the quantum gradients of the quantum functions. So now that we've seen a bit of a background of what differentiable quantum functions are, and that we can include them in arbitrary hybrid quantum classical systems and train the entire model from end to end, let's get into what transforms are. So if you've used a machine learning library like JAX, you'll be familiar with this concept of transforms, maybe not by name, but by familiarity with how you program using something like JAX. So JAX is a very functional machine learning framework, and it's built around pure functions. So you define a function that is deterministic and has no side effects. So the output is always the same if the inputs are the same, and the function doesn't do anything on the side. It doesn't write to a file, doesn't modify global variables, etc. And in JAX, we have this concept called a function transform. So it's a process that maps a pure function to another pure function. So if you can look at this code block on the right, we have a function f of x, which simply takes the sign and then takes the sum of the input x. And an example of function transform here is simply differentiation. So we have the JAX.grad transform below. JAX.grad is taking our function f as input, and it's returning a transformed function, gradient function as output. And we can then evaluate this gradient function with the original input, and this will return to us not the output of the function f of x, but the gradient of the function f of x. So this is common in libraries such as JAX and other functional libraries that are embedded in Python, like like functorch. And it's also a common abstraction that you see in functional languages like Haskell. So another neat thing about functional transforms and why they provide such a rich playground for creating models in machine learning is that they're composable. So here I've got a very similar example. I've got this function that takes the sign of an input and then the sum of that input, and I'm applying 3 transforms in a row. So first, I'm doing just-in-time compilation of this function, which compiles it down to low-level code, which executes in a much more performant manner. Then I'm taking the gradient of this compiled function, and once I've finished taking the gradient, I take the Jacobian. And so in essence, I'm taking the derivative twice, so I end up with the Hessian matrix. So this is a really powerful construct, the ability to arbitrarily compose these functional transforms to build something bigger than the sum of the parts. So that's a very brief introduction to functional transforms as seen through the lens of JAX. What about quantum transforms? So quantum transforms are actually quite common. You just might not have heard them described by that particular name. So a quantum transform, like a functional transform we just looked at, simply maps a quantum function to another quantum function. And this is very common when you realize that this is simply the same thing as quantum compilation or quantum transpilation. So in this particular example, we have one quantum function, and we're applying a quantum transform that converts the C0 to another representation. Here it converts the C0 to Hadamard CZ and then another Hadamard, and we get a new quantum function out of that. So a quantum transform is simply a mapping from quantum function to quantum function, such as quantum compilation. However, we can go beyond this concept. So we saw that quantum compilation simply turns one quantum circuit into another. We can think of a quantum transform almost as a generalization of this. So rather than taking one quantum function to another, it could potentially take one quantum function to multiple quantum functions that are bound by classical processing. And one example of this is, for instance, the parameter shift rule that we discussed earlier. So recall the parameter shift rule is a way that we can take the gradient of a quantum function on hardware, and we do this by evaluating that quantum function at multiple parameter points and then taking a linear connection. So here we can visualize the parameter shift rule as a quantum transform. So we have our input circuit, and we have on this input circuit an RY gate with input parameter X, and this is the parameter that we want to differentiate. So we apply our parameter shift gradient transform, and remember the parameter shift rule shifts the parameter we want to differentiate forward and backward by a shift value S. And so we apply this parameter transform and we get an output, G of X. So this is our transformed quantum function. And this transformed quantum function contains internally two quantum functions, one that shifts the parameter of Ry forward by S, one that shifts it backward by S, and then we simply take the linear combination with the two parameter shift coefficients. So this is an extension of the concept to one where a quantum transform maps a quantum function to multiple quantum functions and classical processing. So I've got a bit more of a formal definition here. So if we go back to the initial definition of a differentiable quantum function, let's say we have a quantum function f of theta with input parameters theta. A transform T with input phi of I is a quantum transform if it maps a quantum function to a set of quantum functions. But it's a differentiable quantum function if this mapping preserves differentiability. So if our input quantum function is differentiable, this transform T is a differentiable quantum transform if the output of their functions are also differentiable with respect to the same input theta. But we can go even further. The transform T might have its own inputs, phi I, that control how the transform is applied to the input quantum functions. So the quantum transform T might also be differentiable with respect to its hyperparameters. And this might be a bit confusing, but I've got an example here that might explain this a bit better. So let's go back to the parameter shift example that we saw earlier. So on the right, we have this pictorial representation of this quantum function transform of applying the parameter shift rule to get the gradient of f of x. On the left, don't worry too much about the details here. I just want to show that this is an example of what defining this quantum transform looks like in a library such as PennyLane. So we're using batch transform to say this is a transform that maps one circuit, one quantum function to multiple quantum functions, and we're creating those internal quantum functions and the classical processing step and returning those. So this is what looks like in PennyLane to actually code up this example of a quantum function to multiple quantum functions transform. And what I've done is I've taken that definition, I've entered that into my Python notebook, and now I want to play around with it. So here I'm creating my initial quantum function, f of x. It has a couple of quantum instructions, a rotation gate, and it's returning a measurement statistic, so an expectation value of Pauli Z. Now I want to apply this parameter shift transform. So I have the parameter shift transform, I apply it to the input quantum function circuit, and I set the shift value, which in this case is s equals 0.2. And now I have my new quantum function that comes out of the output. So this is g of x, and I'm evaluating it, and evaluating this will give me the input. Will give me the gradient of our original function circuit. So we've applied this parameter shift transform. We've got our new quantum function coming out of it, and now we can evaluate this new quantum function. And this is a differentiable quantum transform because the output quantum function, new QFunc, I can take the gradient of that. So I've taken the gradient with respect to our original input parameter x, and it works. So I'm taking the gradient now of g of x, which represents the gradient. So this will be the second derivative. But we can go even further than that. So I mentioned that we can differentiate the output of a differentiable quantum transform. But the really neat thing is we can also differentiate the quantum transform itself. So if you have a look back here, this quantum transform has a hyperparameter s, which is the shift value. And this shift value can be an arbitrary float. So what this means is we can not only differentiate the output, but we can differentiate applying the quantum transform and get the gradient at s. So let's have a look at what this looks like. So in this particular case, I need to create a separate cost function gradient. So this gradient function contains both applying the parameter shift transform with a parameter value s and evaluating that at parameter value x. And now it's as simple as asking for the gradient of the function at both x and s. So this is the gradient of the gradient, so the second derivative at value x. And this is the derivative of the transform. The derivative of the hyperparameter s of the transform. So this is in essence dg over ds. So this is really neat, but why would we want to do this in the first place? So there's a couple of cool reasons why we might want to do this. So if we write our model such that we're using differentiable quantum transforms, we have this really neat ability to be able to now train the model to adapt to the hardware. So we're not stuck in this case where we have a very rigid model and we have to assume that we've written a model that works on a particular noisy setting that we've chosen. Instead, what we can do is we can take these model parameters and encode them within the very same cost function we're optimizing. And what this means is that we're training the model itself alongside the model parameters during the optimization. So if you think back to that previous example, if we're doing gradient descent with that particular cost function, we could do gradient descent on the model parameter x, but we could also do it, on the quantum function parameter x, but we could do it at the same time with the model parameter f, the shift value of the gradient, the parameter shift gradient rule. So the cool thing about this is that we can train the model itself to adapt directly to the noisy hardware backend without the need to separately characterize the device works, what the particular noise looks like on this device. We don't have to worry about porting that to different noisy backends. We can simply train the model at the same time we're training the model parameters. But if we take a step back, there's even a more general way of looking at this. And we see a lot of analogies in this concept of differentiable programming. So differential programming is a new computing paradigm that kind of fell out of the huge advances we've gotten in machine learning tool sets over the last 10 years or so. So with machine learning frameworks, we started off writing very rigid neural networks that had very rigid structure, and we were simply training the weights. But the key insight from all these autodiff frameworks is that we don't have to be restricted to those rigid models or those rigid structures. The entire program, including how we construct the model, is end-to-end differentiable. So since constructing the model is end-to-end differentiable, we can train the model alongside the parameters of the model. So this is a really nice insight, and we're seeing more and more of this happen in the machine learning space. So it's really nice when you're working in an environment such as a noisy quantum hardware device, where the system is potentially too complex for programmers to manually design algorithms or design models, or perhaps the setting is too bespoke. So maybe it alters too dramatically between different hardware devices. So we want the ability to write a very parameterized model once and train that model alongside the hardware. So I think the key takeaway, though, is that with this concept of differentiable programming that's unlocked with differentiable quantum transforms, there's no underlying assumptions to the form of the model. It consists of arbitrary networks of composable parameterized functional blocks, and every one of those functional blocks in the model we can train. So I want to quickly finish just by showing how this integrates with penny lane and what differentiable quantum transforms means in penny lane. So from the very beginning, penny lane has almost been developed directly around the concept of quantum transforms. So if you've used penny lane and you've used QML.grad, QML.metric tensor, QML.adjoint, or QML.control, you have used a transform. And as we've been adding these transforms, we've been trying to keep them mostly composable. And I say mostly because not all transforms return numerics, and so those ones won't be able to be composed. Differentiable, so every transform we add, we try and make differentiable, and usually hardware compatible. And I say usually, most of our transforms, our quantum transforms in penny lane, are hardware compatible, but we have a few that take advantage of simulators to provide a speed boost. So if you're using a specific transform that's simulator focused, then you don't have the hardware compatibility there. Finally, the key thing about penny lane transforms is that they work with the classical transforms that you get from other libraries. So you can use them with jax.jit, jax.vmap, the torch.autograd module, in most cases, even if you're using hardware. So a quick example here, I just want to point out, this is just your stereotypical penny lane program to compute the metric tensor, and there's already tons of transforms in here. So here we're taking the adjoint of a gate, which is a transform. We're transforming a quantum chemistry template, single excitation, to become a controlled template. So that's another example of a transform. And then after we've evaluated within our cost function, we're transforming this quantum function to instead return the Fubini study metric tensor, which is a convenient metric for quantum information. And then finally, we're taking the derivative of this entire function. So we're taking the derivative of the metric tensor of a quantum function. And this should all work on hardware, and it's all differentiable. I mentioned earlier as well that compilation is an example of a quantum transform. And this is also something we've been working hard over the last couple of months to build into penny lane. So I believe the last couple of versions of penny lane now come with a budding compilation pipeline. So we have this QML.compile decorator, which you can apply to your quantum function. And you can provide a individual pipeline composed of themselves quantum transforms. So here I've got one transform that commutes controlled gates to the left, one that fuses single qubit rotations, and one that cancels inverses. So at the moment, we're still building out the quantum compilation pipeline in penny lane, but something I want to emphasize again is that these quantum compilations, we're aiming to get them all differentiable where possible. At the moment, there are no quantum compilation transforms in penny lane that take a parameter. It's very easy to add your own. And if you do add your own and it happens to be dependent on some floating point parameters, then you can train your compilation pipeline on hardware. Another example of a quantum transform that we've just added to penny lane is error mitigation. So this is a collaboration with Mythic from the Unitary Fund, a open source error mitigation library. And what they actually do is they provide various zero noise extrapolation functionalities that you can then integrate into a mitigate with zero noise extrapolation transform that comes with penny lane. So here we've got a transform that takes a Q node and converts it to one that potentially is not, it takes a Q node that's acting on a noisy device and transforms it to have error mitigation according to the parameters provided for the transform. At the same time, we want to make it easy for anyone to come to PennyLane, whether you're someone who wants to play around with what's available, play around with quantum computers, or do hard research. And so what we're also attempting to build out is a set of DIY transform capabilities. So an API to build your own quantum transforms, whether it's a transform that simply maps a single quantum function to another quantum function, like quantum compilation, or something more complex that transforms one quantum function to a set of quantum functions that are then acted on with classical processing. So something I want to quickly point out as well is that we have a blog post that went up at the end of last year, how to write quantum function transforms in PennyLane. Please check it out if you're interested in seeing in more detail how you actually add your own quantum transforms to PennyLane. And another good resource is our documentation. So if you go to the PennyLane documentation and scroll down on the left-hand side, you'll see a qml.transforms package. And this package contains a wealth of different quantum transforms that work across hardware, that are differentiable, and in a lot of cases composable, to play around with the model that you're constructing when you're performing quantum machine learning or building variational quantum algorithms. So I just want to finish and say that we want your feedback. So transforms are still under heavy development. We're really excited by what you can do with differentiable quantum transforms and how they maybe shift the way of thinking of building and programming quantum computers and quantum models and quantum machine learning. But yeah, your feedback is super valuable at this point. So play around with it, check out the blog post, have a read through the documentation, and let us know how it's working for you. If there's something that's missing that you'd like to be able to do, are there transforms you'd like to contribute back? And I just want to also finish by saying that more details are coming soon. So we're very excited that shortly we'll be providing a wider study on what quantum computing with differentiable quantum transforms means and what some of the applications are. And yeah, just a final slide to point out that we have a huge amount of demonstrations across quantum machine learning, quantum computing, and quantum programming. So check out pennylane.ai/QML to explore what you can do with PennyLane today. Thank you.
Thank you, Josh. What an amazing talk. I love the font, the choices, and the use of live coding video is brilliant. Right? Live coding is so dangerous. Just make it appear the case with the video. Fantastic. Joshua, a few questions for you. You're the head of quantum software at Xanadu, right? And a lot of quantum computing, I would argue, is about understanding that interface between classical and quantum in different ways, and that manifests itself in different ways. And I think it makes an appearance in software as well. So there's quantum software is maybe different than software that's not about quantum. In your mind, what are the specific things that make quantum software different than more like traditional efforts in software development?
So I think a big thing is how close quantum software is to the literature. I think this is common across scientific computing to various degrees, that for quantum software and specifically quantum machine learning as well, I think it's very, very tightly integrated with what's coming out, not just in the literature, but what people want to do for research and what they want to be able to do.
And go ahead.
I find this really interesting because it's not just one directional, it's two directional. The quantum software, there can be advances in quantum software that, without realizing, unlock new directions in research, and vice versa. There can be new results in research that unlock new ways of thinking in quantum software.
That's right. And that makes a big component of the work we do, interplay between research and software, right?
Exactly. Yeah.
But then why do you think that is? Why do you think quantum software is particularly tied to like the actual research frontier?
It's a good question. I think, part of it is that a lot of the people working in quantum software come from a previous life or current life in research.
Okay,
So there's a familiarity with what people are doing that ends up becoming part of quantum software. But I think at the same time, we're still trying to work out what quantum software looks like, and we're still trying to work out how it connects to hardware. And the hardware is always changing, and the hardware is also tied into research. So I think it comes in through multiple points. And yeah, in terms of like how you want to, what applications do you want to do with quantum software? How do people want to use quantum software? How do we connect to the hardware that's available on quantum software? How do we make that experience seamless? I think even that still ties in a lot to what's coming out from the literature and the research.
Yeah, maybe it's a manifestation of the fact that it's still early stages to some extent, right?
Yeah.
It's still something that's developing in itself, and so it's an inherent aspect of figuring things out, and maybe that ties it with the research, right? Speaking of early stages, Josh, you are one of the first developers for Penny Lane, right? You were there from the moment there was no single line of code to the first release. Can you tell us a little bit about that journey and about like that? Like, what was going through people's minds in terms of having this idea of creating Penny Lane, and since that inception, how have things actually grown? And if you reflect back on what has been achieved, just if you could just share us some of that journey. Yeah.
I don't think I was there quite from the first line of code not being
Oh,
written.
okay.
I think I joined maybe 2.5 months after. So I joined where there was quite a lot of research and quite a lot of code, even though it
Got it.
maybe didn't see the light of day in its current form. I think it went through a lot of refactors before going public.
And how has that journey been like for you?
Yeah.
So when you look at what the whole code base looks like now versus those early days and all the steps
It's
in
been so much
between.
fun. It's been so much fun. There are so much there are so many aspects of the early days that mirror what happens today. So a lot of Penny Lane was developed alongside development of the parameter shift rule and how we can integrate that into quantum software.
Yeah.
So I think if you go online, you'll see that there's a Penny Lane white paper, and there's also a paper called Evaluating Quantum Gradients on
Analytical gradients, I think.
Hardware. Yeah,
Yes.
analytic. I always get that wrong.
Yeah.
And I believe those two papers went up almost at the same time and came from the same common knowledge, I think. So it was the same project where those two results came out of them. So from the very beginning, Penny Lane was very intrinsically tied to quantum computing and quantum machine learning research. And like we were discussing earlier, that's still the case. A lot has changed at the same time. We have a lot more developers working on it. We've had a lot more releases, and I think we have a very nice vision now. I think it's something that happens a lot, especially with quantum software being such a nascent field, that you're building something before you have all the data points.
Yeah, for sure.
And so you always find yourself in the trap where you want to make those big decisions when you have the least amount of info.
Yeah, that's a lesson you taught me, actually. Yeah.
Yeah, it's something that still happens every day, but I think there's been so much exploration and so much trial and error and so many creative ideas across the entire development team that I think the library's become more cohesive, and a vision is starting to appear of what quantum software could look like in the future. Because I think that's always the goal, right? Not what quantum software looks like right now, but what it looks like in 2 years or 3 years or 10 years.
I definitely agree with that. Josh, you gave a talk at PyCon US, if I'm not mistaken, right? And I think you mentioned this was probably the first talk at such a conference on quantum software. What was that like exactly, and how did the people in the audience react?
I think it was the first talk at PyCon for quantum, maybe not the first one at a PyCon. So like some of the regional PyCons had quantum talks. I think QHack was at one.
Yeah, okay.
I wasn't expecting it to get accepted. I know that the acceptance rate for PyCon is very low. And a lot of people have contributed huge projects to the scientific Python ecosystem, and the Python ecosystem have had talks rejected year after year before getting accepted into PyCon. So the entire time I was like, this won't be accepted. This won't be accepted. And then it was accepted. It was really exciting.
Yeah.
It was really nice to be able to share the work that the quantum community has been able to do with quantum software and within the Python ecosystem.
Amazing. Josh, and all this work you've been doing in the past few weeks have happened from Australia. So you're currently in Australia. I believe the story was you were there around March, April 2020, and have just stayed there. Could you comment on some of the what that has been like and some of the challenges and potential kind of advantages of doing that? I know you have at least one perk, which is you're minutes away from the sea, which I always envy in a good way. But maybe for everyone in the audience, if you could tell us a little bit more about what it's like working with the time difference and in this remote way, just how it's been like for you.
Yeah, for sure. So I think I also mentioned this last year in QHack. I've got vague memories now. But for those who are unaware, I had a very poorly timed or well timed, depending on how you look at it, family holiday scheduled for Western Australia back in March 2020. And I arrived and my return flight got cancelled. I've been here ever since. So I'm a bit of an accidental overseas remote worker.
Yep.
And because of that, I've been attempting to align my schedule so that I have maximum overlap with Toronto. So I've been working maybe 3 p.m. in the afternoon, large break for dinner, and then working late into the night in the early morning.
Yeah.
Which I've always loved. I'm a bit of a night owl. This is how I did my university degree. But yeah, it's hard. It's really difficult, especially when you're cramming so many meetings into a smaller overlap than you would have if you're on the same time zone.
Yeah. That's
right. We recently moved. So I'm still in Perth, Western Australia. We recently moved to a new house that's less than a minute walk from the beach. And it's in the middle of summer right now, like 37 degrees Celsius. So I've been sneaking away to the beach in the morning before my meetings start.
It's a great way to start the day, if you ask me. Excellent. Josh, we have also some questions from our audience. One relatively straightforward one is, do you have any preference for Jack, PyTorch, or TensorFlow for Penny Lane? And in terms of ease of compatibility? This is a question from Mega Dan.
That's a really good question. So it depends what your workflow is looking like. If you're using one of the built-in Penny Lane simulators like Default Qubit, we've worked hard to really optimize that with all of the machine learning frameworks. So in all three of those cases, if you do a variational workflow and you ask for the gradient and you do optimization, we'll activate backpropagation behind the scene, which will end up being a lot more efficient for a small number of, like, I don't know, 10 to 15 qubits than parameter shift. But yeah, it's very much dependent on your workflow. If you swap to external hardware devices and you start using finite shots rather than exact shots, it depends. So some frameworks have better compatibility with Penny Lane in that respect. I do really like JAX because it provides this capability to do just-in-time compilation. It's not something that has full support yet across Penny Lane, but in a lot of cases, you can use JAX with Penny Lane on quantum hardware, and just-in-time compilation is still supported, which can see massive speed-ups if you're doing heavy compilation for the execution.
Yeah, so it's interesting, right? We're tempted to think what's the best, but sometimes there's different tools with different capabilities, and it's important to navigate which ones are best.
Exactly, right? And another thing is, I guess, it's whichever one you like the most, because the framework that you are more comfortable in and brings you joy, you'll find the best environment for writing quantum algorithms.
I fully agree with that. Okay, another question from Gopal Mai. How does Penny Lane compare to other software packages like Qiskit, TensorFlow, Quantum for quantum differentiable programming? Right? And do you know of any analysis that has been done and what has been the result? But I guess generally speaking, can you comment on kind of what makes each special and different?
Sure. That's a really good question. So differentiable quantum programming as a paradigm, I think, is so new that it's difficult to compare. Definitely, we've done a lot of work in Penny Lane to make this front and center. So like I mentioned in one of the slides, if you've been using QML.metric tensor or QML.grad, you've already been doing differentiable quantum transforms and differentiable quantum programming in Penny Lane. I'm not too up to date with how it currently looks in Qiskit. I think in Qiskit, it's a lot more hardware focused and compilation focused. So quantum programming, if differentiable quantum programming isn't front and center. and maybe there's a bit more manual coding in order to do that integration. Although I know they do have PyTorch support. TensorFlow Quantum is another good option. It's very heavily integrated into TensorFlow, and I'm not sure it has in the public version. I'm not 100% sure if it has hardware access. Last time I looked, it was mostly still simulator based, at least in the public version of TensorFlow Quantum. So I think that's at the moment one of the main advantages of PennyLane, that you have this differentiable quantum programming front and center. So that's what you're using as soon as you start in even some of the most basic PennyLane programs, and the high level of compatibility that we support for different autodiff frameworks and hardware and simulators.
Yep. So again, it depends to some extent, right? And
it depends.
Yeah. Okay, this is a question I'm not sure I would know how to answer. It's a bit of a tricky question, but I'm gonna shoot it anyway. Let's see how it, and which is the following. It's a question from Quantum Learn. Josh, are integer operations easier for quantum computing than float operations?
I'm not sure I know how to answer that question, I have to say.
Yeah, but maybe do you find any instances in workflows and some of the programming where making that distinction between ints and floats that has some impact? It's a bit of a nitty-gritty question. Yeah.
I think so. Definitely in classical programming, it makes a difference. If you write an algorithm at the low level in C++, etc., and you choose like int 8 over int 32 or float 64, then you can see massive performance improvements and memory improvements. I'm not sure we're at that stage yet, at least with high-level quantum programming, where there's much
that's a good point.
Okay.
Right. No, go ahead. It's a bit of delay with Australia, I think. So just take it.
I think we're still there's too many levels of abstraction between like PennyLane and the cloud APIs you're submitting to the hardware and the hardware control systems, that maybe this is something that will be come clear in the future. Maybe it's something that doesn't have the same analogy to classical programming and quantum programming.
Yeah, you make me think that I would argue there's also something that makes quantum software unique, is that there's this kind of two branches of whether you look at simulators or hardware, right? That doesn't really apply so much in the classical sense. It's always the hardware that's doing everything. It's the same type of thing. You may change GPUs, TPUs, and so forth, but it's the changes aren't as drastic. Whereas we also have to always navigate the difference between something executing in simulator versus on hardware. Right?
Yeah, and at the moment, even if you're just thinking about hardware, frameworks like PennyLane and Qiskit, I think you're very separate from the hardware control. Maybe this changes in the future as well, and then maybe there is an advantage to using one type of data type over another.
Yep. All right, Josh. Unfortunately, that's time. I could spend much more time talking to you. Thanks so much for the fantastic talk and for answering our questions. And I wish you a great rest of the day. Thanks so much again for joining us.
Yeah, thank you.